Welcome back, students. In continuation with the molecular structure, now today we consider the another feature which is more practical, which is more accurate, because it is one of the modern analytical technique. This video is for education purpose only. No copyright infringement. This copyright belongs to its rightful owner. In this slide, we consider about the introduction of a molecular spectroscopy. Spectroscopy is a technique which is nowadays very useful to study the molecular structures, not only in case of the chemists, but also it is useful for biologists, physicists to confirm the molecular structures and the different reactions in the complex molecules. Now, in the spectroscopy, the interactions between the sample molecules or matter is studied with electromagnetic radiations. And when the matter is the sample molecules, then the technique is referred as molecular spectroscopy. So spectroscopy is simple, that it is the study of interactions between the matter and electromagnetic radiations. You know, sun is very good source of electromagnetic radiations. This electromagnetic radiation is a very broad spectrum, out of which we are considering only three zones or regions, namely ultraviolet and visible region, microwave or rotational region, and infrared or vibrational region. The electromagnetic radiations, as the name itself indicates, the two components are there. One is electric component and another is magnetic component. So this electromagnetic radiations is made up of electric and magnetic components which are simultaneously vary when the radiations are moving from the source. And both these components are found to be perpendicular to each other. These electromagnetic radiations are characterized by frequency, wavelength, energy, and intensity. Now, as I considered initially that the electric component and magnetic component both are perpendicular to each other, and that we will find here in this graphics, the electromagnetic radiation is propagating from a source, and it is also called as sinusoidal wave. It is also called as sinusoidal wave. Red it is the electric component, electric field, while violet is the magnetic field, magnetic component. Now we consider here, in this diagram you will find some notations. C is the velocity of light or electromagnetic radiations, which is measured in meter per second. Lambda wavelength, which is measured in meters. Nu is the frequency, which is measured in hertz, or it can be very similar to that of cycles per second, CPS. Now C0 is the velocity of light in vacuum, and that you know its value is around 2.99776 into 10 to plus 8 meter per second. And we also find here the energy of electromagnetic radiation is given by the formulae E is equal to h nu, where h is Planck's constant. Now we consider each characteristic property in details. First of all, we consider wavelength. Here, electromagnetic radiation is shown in red. The distance between two peaks, successive peaks, or successive troughs, or successive maxima, or successive minima, is referred as wavelength. Or in other words, distance travelled by a complete wave is also considered as wavelength or called as wavelength. It is represented by simple notation lambda. That one trough and one peak that we consider as a complete wave, means one maxima and one minima. If we consider here that, suppose, see here, from this particular point the electromagnetic radiation starts traveling, moving. Here it becomes a complete half cycle up to this point, and again it becomes the next half cycle. Here a complete wave is here travelled. So the distance travelled by a complete wave, means from this to this, is considered as a wavelength, or distance between two successive maxima or two successive minima is considered as lambda or wavelength. It has the unit of length measurement, may be measured in centimeter, maybe in meters. If it is smaller, then it is millimeters. If it is still smaller, microns, then millimicrons, then angstroms, or in nanometer. And conversion of each towards meter or centimeter is well known. The another characteristic we consider is frequency, and that is represented by nu. Frequency, that is represented by nu. Now what is the frequency? Frequency is the number of complete waves. Number of complete waves. Complete wave means starting from this to this, it becomes a complete wave. So number of complete waves passing through a given point per second is the frequency of that electromagnetic radiations. The number of complete waves passing through a given point in 1 second is considered as frequency of electromagnetic radiations, and it is measured in cycles per second. Number of cycles per second. So that is called as hertz. So hertz or cycles per second is the unit of frequency that we considered here. It is also well known that y is represented here in this graphics, and that is this distance of the maxima from this particular x-axis, what we call, and this distance of maxima is called as amplitude. If we consider this is the half cycle or half circle, and this is the next half circle, it comprises, suppose here in this fashion, so it forms a complete circle. So when we consider that it is moving a complete cycle, so this is nothing but your then radius. This is nothing but your radius, means amplitude is considered here in this particular way, height. Now another term that we consider here is c, speed of light in vacuum. Means speed means velocity. Velocity of light means electromagnetic radiations. This is electromagnetic radiation, which is having the same properties as that of visible radiations. Means it is moving in a straight line. It is moving in a straight line. So see here, arrow is shown. It is moving in a straight line, starting from the source. And hence it is also considered as the sinusoidal wave or electromagnetic radiations. And these electromagnetic radiations are traveling in a straight line. When it is reflected or when it is refracted by some obstacles, then after reflection or after refraction, again it is traveling in a straight line. So in this fashion, the property of the visible radiations is similar to that of the property of electromagnetic radiation. Now we consider here speed of light or velocity of light. It relates with the wavelength and frequency. When we take the product of nu into lambda, this product is considered, or it is equal to speed or velocity of light. So c is equal to nu lambda, means the product of the wavelength and its frequency is always remain constant, because c, velocity of light, is constant number, and that is around, that we have seen, 2.99776 into 10 raised to plus 8 meter per second. This is a constant number that we find. Means the product of wavelength and frequency of a given electromagnetic radiation is always constant. Now, from this particular simple equation that c is equal to nu into lambda, it becomes very clear that nu, frequency, is inversely proportional to wavelength, or wavelength is inversely proportional to frequency. And that's why if the wavelength is smaller, the frequency associated with the radiations is higher. If a wavelength is higher, the frequency associated with the radiations is smaller. The another term that we are going to find it here again, and that is more important in the spectroscopy, and that one is wave number, and it is represented by nu bar. Now see here, nu bar is given as a reciprocal of wavelength, that is 1 upon lambda. But this can be defined as number of waves. You can also correct it as a number of complete waves present per centimeter. Number of complete waves present per centimeter is called as wave number, and it is measured in centimeter inverse. if we measure the wavelength in centimeter, then wave number is measured in centimeter inverse. In spectroscopy, it is important that all the parameters like frequency, wave number, wavelength, and also energy that we try to measure in centimeters, because this is the important unit. Now we consider here how this energy is quantized. The total energy of the molecule is considered as a summation of translational energy and internal energy. Internal energy is also considered as summation of rotational energy, vibrational energy, and electronic energy. All these energies means electronic, vibrational or rotational. They are in the discrete fashion. They are fixed. They are quantized. It means the internal energy is quantized, and in other words, the total energy associated with the molecules is also quantized. Max Planck suggested that each form of energy is quantized. Quantized means it is having fixed value. It is having fixed value. And this fixed value is considered as these molecules are regarded as possessing certain discrete energy states, means in the discrete different energy levels these molecules are present. Now this is the Max Planck equation. This is very important, and this is the basic equation of the quantum theory. In this equation you will find energy is directly proportional to frequency of the electromagnetic radiations. It means if the frequency of electromagnetic radiations is smaller, energy associated with the electromagnetic radiations is also smaller. If the frequency of the radiations is greater, energy associated with the electromagnetic radiations is also greater. And here H is universal Planck's constant. It is the Planck's constant, and E given by E is equal to h nu. This is also you may call the proportionality constant here. Now see here, again we can interrelate this nu from this simple equation C is equal to nu lambda, and we rewrite the equation for quantum of energy E is equal to h nu as E is equal to hc upon lambda, because nu is equal to c upon lambda. If we rearrange this equation and substitute here in the previous equation of E is equal to h nu as in terms of nu here, we get hc upon lambda. It means this is the important equation which relates here the wavelength and energy, and you find here that wavelength is inversely proportional to energy, or energy is inversely proportional to wavelength of electromagnetic radiations, because h is Planck's constant, c is velocity of light, it is also constant, so E is inversely proportional to wavelength. Now we consider here the relationship between the energy and wavelength, as well as the wavelength and frequency, and or energy and frequency. Now we consider that the total energy is quantized associated with the molecules, and then the molecules are present in the different energy states. This is one of the lower energy state, E1. This is one of the higher or excited energy state, which is having more energy, so it is considered as E2. So here, if there is a transition from lower energy state to higher energy state, some energy should be get absorbed here, or if there is a excitation from this particular higher energy state to one of the lower energy state, means here some energy or electromagnetic radiations are given out, emission is seen here, so some energy is absorbed while excitation from lower energies to higher energy state, some energy is given out when the molecule is excited from higher energy state to one of the next lower energy state, and this energy is given by delta E. Delta E is equal to E2 minus E1, and we consider this delta E is equal to h nu, and this is the same as hc upon lambda or hc into nu bar. Nu bar is the wave number, that is 1 upon lambda. So this is a simple equation of a simple energy expression, that is difference of energies, and here you will find the delta E is equal to n h nu, where n is Avogadro's number here. So if we consider the 1 mole of any substance, it contains Avogadro's number of particles, and therefore total energy associated with the 1 mole of any substance is considered as the molar energy, and this is measured in joule per mole. Joule per mole. And if we consider that this equation, first equation, E is equal to h nu, this is the single quantum, and this is the number of molecules present in the quantum, and those are the Avogadro's number. So delta E is equal to NH nu. Its unit joule per mole. This is the energy. So energy may be measured in ergs, maybe in calories, maybe in joules, and if it is for a mole, then it is ergs per mole or calories per mole or joule per mole. And now in spectroscopy, as I told initially, that the energy units not only joule or not only calorie or not only ergs, but hertz means cycles per second or centimeter inverse, or even sometimes electron volt also. Now see here the higher energy and lower energy. Higher energy means higher frequency, lower energy means lower frequency. Higher energy means short wavelength and low energy means longer wavelength. So these are few regions that we find, that is gamma ray region, X-ray region, ultraviolet region, visible region, infrared region, microwave region, and radio frequency region. This radio frequency region is from low energy, while gamma ray region is from high energy, and all these are in between high energy and low energy regions. These regions are of electromagnetic broad spectrum. These are the regions. Now these regions do not have the very sharp boundaries. They are having diffused boundaries, and we classify them into the different regions here. Now these regions are shown here in terms of frequency range, in terms of wavelength range, and out of this, here we specify the visible spectrum. At the bottom of this graphic, we find the visible spectrum. Here 700 nanometer and here 400 nanometer. Wavelength is given, that of visible region. So see here, towards this side ultraviolet light, towards this side it is infrared region. Means this is not fixed boundary, as I told. This is also not fixed boundary, they are diffused one in other. So visible spectrum is approximately ranging from 400 to 800 nanometer, or sometimes it may be called as ranging from 10⁻² to 10⁻³ nanometer. And in each region of a electromagnetic broad spectrum, this type of different transitions or motions are observed. In this nuclear, this is inner electron, outer electron, outer electron. Outer electron means valence electrons from the valence shell. Inner electrons means inner core electrons. Now here the molecular vibrations are considered. Now here the molecular rotations are considered. And here nuclear spin, which is flipping from one to other states. Now here you will find the two energy states. One is the lower energy state, another is the higher energy state. And this blue line, blue dark line, is considered as the ground electronic state. This is not only the very sharp line which is shown here as a ground electronic state, but it comprises the series of different vibration energy states also. From the lower electronic state, there are, suppose this 1, 2, 3. These are the lower vibration state. In the excited electronic state also you will find this is 1, 2, 3. These are the excited vibration energy states. So, in the electronic state, you will find there are a series of vibration states, and in between the two vibration states, the green lines, you will find again the red lines which are very closely spaced, and those are called as rotational energy states or rotational energy levels. So, you will find that the difference between the two electronic states is greater than that of difference between the two vibration states, than between the difference between the two rotational states. And from this it becomes very clear that how these transitions are accounted. Now here we consider the absorption spectroscopy, means the radiations of light will be absorbed by the molecule sample or matter, and here you will find emission spectroscopy. The radiations of light will be given out from the sample in terms of the maybe higher wavelength or maybe the lower wavelength. And here, as I told initially, the intensity is one of the factor, which is one of the character that may be absorbed or that may be evolved. Here, this is the spectrum that you will find of intensity versus frequency for absorption spectroscopy, and corresponding here for emission spectroscopy. So here in absorption spectroscopy you will find lower peak, while in case of emission spectroscopy the intensity of light emitted is higher. While this zigzag line that you will find is considered as noise or baseline. Here you will find some noise, but nowadays the spectrometers do not record this noise because it is already overcome. Now here in case of spectrometers, those are the devices which measures the spectra. Maybe the IR spectra, maybe the rotation spectra, maybe ultraviolet spectra, maybe Raman spectra, maybe your mass spectra. The different types of spectra one can record. All these spectrometers have the four basic units. The first one is source of light. Here you will find source of light, which depends when the microwave spectrometer is account, then definitely the source should emit the microwave radiations from the electromagnetic spectrum. The another is the sample holder. It is also called as cuvette or cell. The third one is the monochromator, which comprises this dispersing element and the different mirrors, entrance slit, exit slit, etc. This is called as the monochromator. The monochromator is a device which gives us the single wavelength of light, while other radiations are get absorbed by the filters. And the last important here, the unit is fourth unit is detector. This detector is also different in the different spectrometers. One may have the simple detectors like the based on the photo electron effect, maybe the thermal effect. So the different types of very sensitive detectors are used nowadays, which are responsible to measure the absorbance of the light radiations, which can be plotted here on y-axis, and frequencies are plotted here on x-axis. So you will find here the red line, which is shown as a spectra, which shows here the three peaks for corresponding the three different specific functional groups in that molecule or 3 different specific atoms in that molecules. Now here the blue line is also shown, which is the baseline. Now here you do not find any noise, which is very clear, very straight line. Noise is completely absent here, and that's why the intensity, or in other words absorbance of the peaks, will be appropriately or correctly measured. Now these are the different spectra recorded that we will find: absorbance, percent transmission versus frequency or wavelength. Spectral features that one can consider: the band position gives us the different functional groups which are present at that particular specific position, which indicates the different types of functional groups which are present in the molecule. The peak width or bandwidth we consider for the spectral line, that broadening is accounted, that is also due to the different factors here: collision broadening, Doppler's broadening, and lifetime broadening. Here the intensity is important. This intensity is measured in terms of absorbance, and this absorbance is depending on these 3 factors: transition probability, population of states, and path length of the sample. And this path length of the sample we measure in terms of the the path length of the sample we can measure by using this particular equation: A is equal to epsilon L into C, where A is the absorbance, which is defined in terms of this equation minus log of I upon I0, where I0 is the initial intensity of the radiations, I is the intensity of the radiations which is transmitted from the sample, epsilon is the extinction coefficient or proportionality constant, L is the length of the sample, and C is the concentration of the sample. So absorbance is directly proportional to length, or absorbance is directly proportional to concentration, and this equation that we call it as Lambert's BS law. It means here in the basic introduction to the molecular spectroscopy, we considered today the 3 things: that what is meant by the molecular spectroscopy, what is meant by the electromagnetic radiations, what are the different characteristic features which are associated with the electromagnetic radiations, and each in detail, along with the spectrometer and its 4 basic units. Now, today we stop here along with these particular features. Next time we continue the first spectroscopic technique, and that is rotational or microwave spectroscopy. Today we stop here. Thank you.